Hey everyone, and welcome to this explainer. Today, we're literally going to unlock one of the absolute fundamental cheat codes in all of physics. And don't worry, we've distilled this topic down so it's perfectly sized and paced for your YouTube viewing, giving you exactly the high-yield information you actually need. We are diving deep into scalars and vectors, and we're going to see exactly why direction fundamentally changes the way we measure and understand, well, the entire universe around us. Let's get right into it.
Section 1. The 60-kilometer question. So let's skip the dry, boring textbook intro and jump straight into a real-world scenario that honestly might just break your common sense. We're going to look at a situation where two completely different answers can both be entirely correct, just depending on which set of physics rules you're playing by. Imagine you're on a road trip, but you aren't just driving on a straight highway. You're actually driving around a giant, perfectly circular track. You finish one complete lap, you check your car's odometer, and it clearly shows you've traveled exactly 60 kilometers. The big question is, does the direction you went actually change anything about how physics views your trip?
Surprisingly, it changes absolutely everything. I mean, sure, physically, your car traveled a distance of 60 kilometers, but your actual displacement, which is your net change in position, is exactly 0 kilometers, literally 0, because you ended up exactly where you started. Your net change is just nothing. Now, how can you travel 60 kilometers but mathematically go absolutely nowhere? Well, let's figure that out. Section 2. Meet the scalars. To understand why that 60-kilometer trip resulted in exactly 0 displacement, we first need to meet team number 1 in the physical world. Let's look at the simpler side of measurements. A scalar quantity is a physical property that's fully specified by its magnitude alone. What does it actually mean? It means it just needs a number and a unit to tell the whole story. It has size, but absolutely 0 concept of direction. It genuinely doesn't care about north, south, left, or right.
Just think of everyday things. The mass of your backpack sitting on the floor at 5 kilograms, the temperature of your room at a nice, comfortable 25 degrees Celsius, or even the 12 seconds it takes to walk down the hall. None of these require a direction to make sense. I mean, if you were to tell someone, hey, my backpack has a mass of 5 kilograms north, they are going to look at you like you're crazy. Things like energy, volume, density, these are all perfectly happy just being a single number and a unit.
Section 3. Enter the vectors.
Now, let's flip over to the other half of the physics universe, where things get, well, a lot more dimensional. A vector quantity is a physical measurement that has both magnitude and direction. To fully describe a vector, you absolutely must state exactly how large it is and exactly which way it's pointing. If you only give the size, your information is basically completely useless. Think about it. If I tell you to push a heavy box with 20 newtons of force, your immediate follow-up question has to be, okay, but which way?
What's really fascinating here is how vectors map directly to the forces we physically feel every single day. Take weight, for example. It isn't just a number popping up on a bathroom scale. It's gravity constantly pulling your mass downward toward the center of the Earth. Or velocity, right? Like a runner moving at 8 meters per second due east. Acceleration, momentum, magnetic fields. All of these absolutely require a directional compass to even exist properly in our physical equations.
Because direction is such a big deal here, we visually represent vectors with simple arrows, and the rules are incredibly easy. The length of the arrow represents the magnitude, or the size. So a longer arrow means a bigger push, a much faster speed, or a stronger force. And the arrowhead, that points exactly where the action is happening. In a lot of your textbooks, you're also going to see vectors written in bold font, or maybe with a tiny arrow drawn over the symbol. That's just a constant reminder that, hey, direction is in play here.
Section 4. The Great Physics Showdown.
Okay, it is time to put these two teams head-to-head to clear up some of the most common misconceptions out there. By putting scalars and vectors side by side, we are going to fix the exact issues that always seem to trip students up on exams. Let's start with distance versus displacement. Just like our circular track road trip from earlier, distance is a scalar. It cares about the whole winding journey, every single twist and turn you took, just blindly measuring the total path length traveled. But displacement is a vector. It only cares about the shortest straight line distance from your start point to your finish point, pointing in a specific direction. So again, if you end up exactly where you started, your displacement is literally 0.
Next up, we have speed versus velocity. Now, speed is a scalar. It's just how fast an object moves, like saying 8 meters per second. But velocity is speed in a given direction, like 8 meters per second due east. And honestly, this brilliantly illustrates one of the trickiest concepts in motion.
Remember that car moving at a constant speed of 60 kilometers per hour around the circular track? It actually has a constantly changing velocity. Crazy, right? But think about it. To stay on the circular track, its direction keeps shifting. So you have a constant speed, but a constantly changing velocity.
And here is a massive one, mass versus weight. People mix these up all the time. Mass is a scalar. It's the amount of actual matter in a body, measured in kilograms, and it is perfectly constant everywhere. Your mass stays exactly the same whether you're sitting in your living room or floating in deep space. But your weight is a vector. It's the actual physical force of gravity acting on that mass, always pointing straight down to the Earth's center. If you were to teleport to the moon right now, your mass wouldn't change one single bit, but your weight would drop dramatically because the vector force of the moon's gravity is just so much weaker.
Section 5. The math of direction. So, how do we actually combine these quantities out in the real world? Well, you can't just mash vectors together like normal scalar numbers on a calculator. You actually have to do geometric addition to find what we call the resultant vector. If forces are working together in the exact same direction, you just add their magnitudes directly. 4 newtons plus 3 newtons equals 7 newtons. Super simple. But if they're in opposite directions, if they're fighting each other, you have to subtract them. 4 newtons pulling right minus 3 newtons pulling left leaves you with a resultant of just 1 newton to the right. And what if they push at right angles, completely perpendicular to each other? That's when you bring out a little geometry cheat code called Pythagoras' theorem. A 3 newton force and a 4 newton force at right angles give you a 5 newton resultant force. Direction literally dictates the math.
Section 6. Your final challenge.
We've covered some fantastic ground today, fundamentally changing how we measure reality. So let's lock it all in with a quick visual summary. Honestly, take a screenshot of this summary right now. Seriously, do it. This is the ultimate cheat sheet you are going to need for your physics exams to remember exactly why direction matters. Scalars are magnitude only. Vectors add that crucial direction. Scalars use simple arithmetic. Vectors require geometric addition. Understanding the differences here is exactly what separates the students who just memorize physics from the ones who truly understand it.
And that brings us to your final challenge for this explainer. Imagine a hiker walks 3 kilometers east and then turns and walks 4 kilometers perfectly north. I want you to calculate 2 different things based on everything we just learned. First, what is the total distance traveled? And second, what is the magnitude of their displacement? Work out the math, drop your solutions down in the comments below, and let's see who truly grasps the incredible power of vectors. Keep questioning the world around you because, as we've seen today, just adding direction can change the entire equation. See you next time.